And today we have Siddhartha Sahi, and he's going to talk about the generalization of Macdonald polynomials. Thank you for coming.
Yeah, okay, hi. So thank you, Dan. Thank you, Slava, for inviting me. And I'm very happy to talk about this work. This is joint work with Jasper Stockman and Vidya Venkateswaran. You may know one or both of my co-authors. It was completely motivated by this very nice work on Weyl group multiple Dirichlet series that several people here were involved in. And basically, I think it started when Gautam asked me if I had some Hecke algebra type explanation for these Metaplectic Whittaker polynomials. And I felt that there should be some connection, but I couldn't see it. And, I attended a few of these meetings on multiple Dirichlet series, and just couldn't sort of bring it together. And then together with Jasper and Vidya, we managed to connect the dots, and it's extremely beautiful. So this is what I want to explain. So I won't say very much about multiple Dirichlet series because this the seminar is mostly about the combinatorics of these local Whittaker functions and and things of that ilk. And also, certainly, I'm not an expert on multiple Dirichlet series, and the arithmetic is for sure very, very interesting, but I don't have anything special to say about that. Okay, so I want to explain how to think about all of this stuff from the point of view of double affine Hecke algebras. And these metaplectic Whittaker polynomials, they certainly have lattice model interpretation. So there's some question whether you can do that for these things that I'm describing, these polynomials. There is an alcove walk type of interpretation, which Jason explained in his lecture earlier for type A. And yes, okay, and possibly there's something similar in general. Okay, so let me try to explain what's what after this long setup. Okay, so let me just talk about Macdonald polynomials. So it's just some remarkable family of functions. And they depend on many, many parameters. Well, not that many, maybe q plus 2 or 3, maybe as many as 5 in some case. And then if you suitably specialize them, you get many different families of special functions that are of some importance in the representation theory of reductive groups. If you specialize the parameters in some way. And so this includes spherical functions, which was, I think, Macdonald's original motivation, but also Iwahori Whittaker functions, although there is a slight twist to do that. Never mind, it's a well understood twist. Okay, now in turn, these Macdonald polynomials can be, and so these Macdonald polynomials look like they're more general than representation theory, but in fact they can be caught or understood in terms of a certain specific representation of Cherednik's double affine Hecke algebra, which I call, well, fracture H. And this double affine Hecke algebra has a representation on the group algebra X of a lattice L. And I will explain all of this in a moment. This representation, which I recall below, in the subject is called the polynomial representation of this double affine Hecke algebra. Okay, so now let me explain the generalization. And so these Whittaker functions, they can be, as I said, they can be generalized to the setting of metaplectic covers of reductive p-adic groups. And these play a key role in this theory of Weyl group multiple Dirichlet series. These generalizations. Okay, so what's the main point? So we will show that Macdonald polynomials also have a corresponding generalization. These are the generalizations of Macdonald polynomials that I'm talking about. And they can be understood via a representation of the Hecke algebra, of the double affine Hecke algebra, I call it pi sub g, on the group algebra Q of the additive group of the vector space. So the polynomial representation was just on the group algebra of L. Now you want to take the group algebra, you go to the additive group of the vectors. So you go from the lattice to the vector space, and you just think of it as a group under addition and look at the group algebra of that. Okay, so it's some huge space, but anyway, that's what seems to be relevant. And then you have a representation on this, which is called pi sub g, depends on some g that I will explain later. Okay, so I'm going to think of, I'm going to call these elements of Q. So previously, when it was just the group algebra of the lattice X, so the elements of X were polynomials, the elements of Q I will call quasi-polynomials. Okay, and I'm going to call pi g the quasi-polynomial representation. Okay, so I'm going to now recall the basics of Macdonald polynomials and then explain our generalization. But I just wanted to explain what is a stage. Any questions? Okay, so if there are no questions, I will continue. Okay, so what is this lattice? So let's take an irreducible affine root system of untwisted type. So what Katz called XR1, affine 1. Okay, and we fix a standard invariant form. Kac-Moody theory, you take the norm of alpha squared equal to 2 for long groups. Okay, now let W be the Weyl group of this affine root system, and let L be its co-root lattice. So that's what the lattice L is. It's the co-root lattice of an untwisted affine root system. Okay, so the double affine Weyl group is, by definition, the semi-direct product of W with L. So why is it the double affine Weyl group? Well, the point is that W is already an affine Weyl group, and it's a semi-direct product W0, semi-direct product with L0. Okay, and where W0 is the Weyl group of this underlying finite root system, phi 0, and L0 is its co-root lattice. So, okay. All right. So, oops. Where am I? Yeah. So then, this W has 2 lattices. L actually has 1 dimension more than L0. Let me explain that. So let's fix a choice of simple roots. Let me call them alpha 0, alpha 1 through alpha r. And I choose them so that alpha 1 through alpha r are simple roots for phi 0. Okay, then this alpha 0, which is the affine root, it's of the form delta minus phi, where phi is the highest root for phi 0. And this vector delta is a null vector. Namely, it satisfies the norm of delta is equal to 0. If I'm going too fast, please slow me down. Just ask some questions. Otherwise, I hope things are fine. I'm trying to explain things. Maybe trying to explain. Yeah. If I'm explaining too much or too little, just let me. Okay. And now the lattice L is in fact isomorphic to the lattice L0 direct sum Z times delta. That's the story of these untwisted affine root systems. Okay, so therefore, this, what I was calling the double affine Weyl group, it's sort of an iterated semi-direct product. First, I have W0 semi-direct product L0, and then that semi-direct product with L0 plus Z delta. So in particular, this Z delta, so let me just say a little bit more about the structure, that this Z delta is central in the double affine Weyl group, and W contains 2 copies of the lattice L0, and there is a commutator pairing of the 2 lattices into Z delta. So there's a little copy of the Heisenberg group stuck in there. Okay, so now let me explain. So I explained to you what is the double affine Weyl group. And now let me explain to you what's going on with the double affine Hecke algebra. So this double affine Hecke algebra was H sub k. And k are certain parameters, and let me explain them now. Okay, so now suppose F is a field, and yeah, so I was talking about the group algebra, but let's actually fix a field F. And let X equals little x to the lambda be the group algebra of L over F. So I will use exponential notation so that I can, yeah, the multiplication will correspond to, it's the usual way. If you want to talk about the group of the algebra of the lattice, it's better to use exponential notation. Okay, so now the double affine Weyl group acts naturally on X. Well, I mean, it's a semi-direct product, so there is an action, just a natural action. And so now the polynomial representation of the double affine Hecke algebra is a deformation of this W action on X. So I'm going to give you a precise definition, but I'm going to cheat a lot. So let me explain. So to define this deformation, we choose some parameters K alpha for alpha an affine root. And I want them to satisfy K sub alpha equals K sub beta if the norm of alpha is equal to the norm of beta. And I will also write Ki for K alpha I. So alpha I, as you remember, were simple roots. Okay, so there are not so many different lengths. There's at most 2. So this means that there are actually just 2 distinct K parameters, even though I'm putting all kinds of subscripts on them. Okay, but 2 is more than 1. So in metaplectic Whittaker functions, there's just 1 k parameter. Here, the theory can have 2 k parameters. Okay. All right. So the double affine Hecke algebra H can be simply defined as the algebra of operators on X generated by the following. First, multiplication operators. So x mu, x upper mu, x by x upper mu times x to the lambda equals x to the lambda plus mu. So that's the sort of the undeformed action of the Weyl group of the lattice L. And all of the beef, so to speak, is in the divided difference operators. So these are operators T0, T1 through TR, and they act as follows. Ti of x lambda is ki x to the si lambda plus ki minus ki inverse, and 1 minus x to the lambda alpha I check over 1 minus x alpha I check times x lambda. Okay, so this is the double affine Hecke algebra defined in its polynomial representation. And I would say that alternatively, one can define this double affine Hecke algebra H equals HK abstractly via generators x mu and ti. Okay, so I'm not giving you that definition, but there is such a definition. In fact, okay, there is this very cool definition. So I have a long paper with Bogdanian, which looks at the abstract definition of the double affine Hecke algebra, in fact, with a Coxeter type presentation, and that's related to congruence groups. So there's some automorphisms corresponding to congruence groups, subgroups of SL2Z, and this is sort of a long paper, like maybe 9. So it just appeared in the memoirs. But right now it's not relevant. So I'll just say that this is the definition. I mean, sorry, I'm saying that there is a definition. And then this formula 1 that I write down is the polynomial representation pi of h, which turns out to be faithful. Okay, so is it clear what I'm explaining and what I'm not explaining? So if you didn't have a definition, you could just take this as the definition.
So I have a question. The second column of the lattice is contained in the subalgebra generated by T0 up to R, or it might not.
Exactly.
It might not quite be if there's a extended affine Weyl group.
Yeah.
Right. So if it's just a co-root lattice, then it would be contained in can you do these generate the?
Yeah. So okay. So the point is that there is a precise. So okay, you can. So sometimes for various purposes, for example, if you're looking at GLN, you might want to look at extended affine Hecke algebras, double affine Hecke algebras, and this is fine. But one dirty secret about extended double affine Hecke algebras is the extension doesn't deform at all.
Okay, and then I have a related question, which is the other copy of the lattice. Does that have a nice formula for its action?
So I think I will explain that shortly.
Okay.
But I'm just defining the double affine Hecke algebra, and you're asking for some more.
Okay. All right. Thank you.
I mean, I think you're asking us just the right questions about more of the internal structure of the double affine Hecke algebra, and I will explain that shortly.
Okay, thanks.
I hope I will be able to explain it shortly, but that's my intention. Any other questions?
So, so I was just wondering, why are we calling this the polynomial representation? Is that?
This I will also explain in a moment. And I'll explain why we're calling them quasi-polynomials also. Just give me a moment. But, you know, okay, good. All right. So here it is. So I have this isomorphism, L is L0 plus Z delta. So if I have an element of X, I can regard it as a Laurent polynomial in X1 through XR, and then also Q equals X to the delta. Right? So yeah, X1, X. So since it's a co-root lattice, you know, it's spanned by alpha 1 check through alpha R check, and Q equals X delta. So in fact, this Q, which is X to the delta, is central for the H action. So one usually considers this P to be a Laurent polynomial in the Xi's with coefficients in F in the field F of Q. So the double affine Hecke algebra representation H is more precisely on Laurent polynomials with coefficients in the field F of Q. Does that answer your question, Andy? Okay.
Yeah, thank you.
You're welcome. And one can also take the KIs, which are some parameters in the field F. We could take them to be generic. What that means is we can just work over the field K, which is rational functions in the Ki and Q with coefficients in the rational numbers. And so you can just work there. Okay, so now let's talk about what Dan was asking. So let ordinary H be the subalgebra of this script H, the double affine, generated by T0 through TR. Okay, so then this ordinary H is an affine Hecke algebra, which means that it's a flat deformation of the group algebra of the ordinary W, which was the semi-direct product of W0 with L0. So what does it mean that it's a flat deformation? So more precisely, it means we have a vector space. We have a tensor product decomposition. H is H0 tensor Y0, where H0 is the finite Hecke algebra generated by T1 through TR. And Y0, let's call it Y to the kappa, little y to the kappa, is kappa and L0 is again isomorphic to the group algebra of L0. But this is different from the x's. You have some y's here. You also had an x to the delta. So, okay, and now these operators, I'll call them capital Y sub k, which are the images in the polynomial representation of little y to the kappa. They form a commuting family of operators in X called the Cherednik operators. And if we work over the generic field, let's say where the KIs and Qs are some parameters, then the Y kappas can be simultaneously diagonalized in X on the space of polynomials, and the joint eigenspaces have dimension 1 over K. If you specialize the parameters in some way, you're going to run into trouble, but you can control that They're suitably generic, but let's just take them to be completely generic for the moment. We'll worry about specializations later. And these simultaneous eigenfunctions are the Macdonald polynomials. More precisely, they are what are called the non-symmetric Macdonald polynomials, but I'll just call them Macdonald polynomials. Any questions? Okay, so that's sort of the basics of the Macdonald-Cherednik theory. Okay. All right. So now, what about this? What's going on here? I don't want to. Are you seeing this thing? Oh, okay. That made it go away. Okay. So now let me explain what is a quasi-polynomial representation pi g. So this depends on some g parameters. So let me explain what are g parameters. So the g parameters, they're like the k parameters, but they are actually functions. So the k parameters were some specific elements of the field f cross. The g parameters are functions from the real numbers to f cross. Again, they're indexed by the same data, alpha and phi. And again, they have the same sort of restrictions that g alpha is equal to g beta if the length of alpha is the length of beta. Oops. And we assume the g alphas are periodic. So they're really functions on R mod z. We assume that, I mean, so it's not a group homomorphism, but it's okay. Doesn't satisfy additivity, but G0 is 1 and G of minus S is G of S inverse. And so it understands the identity and the inverse, but otherwise it's kind of arbitrary. That's the thing that shows up. So these are the G parameters. Okay, so again, I would say, notice there are at most 2 distinct G functions, but 2 is again more than 1. And so when you have, I mean, these are, okay, these will become Gauss sums and then you don't make the distinction. All right, so let's say, so Q, let Q be the group algebra over F of the additive group of the real vector space spanned by the coroots, the affine coroots. So the elements of Q, they are finite F linear combinations of formal exponentials x to the e in capital E. Okay, so these are quasi-polynomials, finite combinations of things of this sort. Okay, so what's this quasi-polynomial representation? Well, first, for E and E, I define some new function hi of E, which is, okay, so E is it's a linearization of the coroot lattice. Anyway, I can do this pairing with roots. And I take G alpha sub I minus alpha I E quantity squared. So it's kind of cooked up to make later formulas simpler. But that's the thing you have to do. If you want to keep things, yeah, you want to kind of distribute the pain. So this is what the hi of E is. And then I define G sub I of E, So maybe I should have used a different letter somewhere, but in any case, this is what's relevant. So it's ki if alpha I is in Z, and otherwise it's just this hi. So the only information from the G alphas that's going to survive is the GI of these. Okay, but it's like different things for different. Okay, so it's some definition. It's moderately complicated, but this stuff was extremely complicated, so I'll settle for moderately complicated. All right. Any questions? So if you want to ask something about this, I can.
Siddhartha, do you have a second example of a function that's not a Gauss sum for G alpha that you want us to think about?
No, but there should be one. So let's talk about that. Right. So maybe I don't know. I mean, I was kind of asking around. I was asking Sol. He didn't know. But maybe you'll have something to tell me, or at least we can try to discuss it together. Certainly, the just affine Hecke algebras with unequal parameters show up in the work of. I mean, some of them actually show up in the work of Lustig and Kato and so on. And so why not double affine Hecke algebras? Why not Gauss sums? And why not whatever? Right? One can but hope. But I'm just discussing some algebra and combinatorics. Yeah. So yeah, I'm just trying to make things as simple as possible, but no simpler. Okay. So it's clear what so GI is a function. There's like one or two functions on R, periodic functions of R taking values in the units in my field. Well, non-zero units in the field. Okay. All right, so now what's the quasi-polynomial representation? So here is the cool thing. Here's kind of the non-trivial thing that comes in. So I'm going to write the usual notation for the floor of a real number. It's the integer part. And now here's our theorem. So the formula is pi g of x mu is x to the e plus mu. So this thing, nothing happened, no dependence on g. And this expression, pi g of ti of xe is gi of e times x to the si of e plus ki minus ki inverse, 1 minus, and here you have a floor. Then alpha I checked over 1 minus x alpha I check times xe. This defines a representation of H on Q. And this is the quasi-polynomial representation. So I never kind of gave you generators and relations for H. So if you just were to go and check this, you would be kind of hard put. But there are generators and relations, and you could check this. But that's certainly not the way to prove this, because that's just a perfectly it would be an unenlightening way to try to prove this. But the thing is that there's a natural constructions. Yeah, I'll say a little bit. But that's the main thing. This is the quasi-polynomial representation, where so if this representation is certain. I mean, the space Q is huge, absolutely enormous. So this representation is highly reducible. Okay, so it has some uniform formulas, but it's highly reducible. If my E happens to be in L, so E was something in capital E, if E was in the lattice L, then 4, the formula 4, actually just becomes 1. All of the dependence on the G parameter drops out. You only have the K's in this expression, and also the floor disappears. So it becomes the, so what this means is literally that the polynomial representation pi is a sub-representation of the quasi-polynomial representation. Okay, somewhat more generally, let script O be an orbit for the action of W on E of the finite Weyl group. Sorry, of the affine Weyl group on E. And let XO be the span of these quasi-monomials where the exponents lie in a fixed orbit under the affine Weyl group. So then this XO is stable under pi G. If you look at the formula, you can see that you never leave this affine Weyl group orbit of exponents. So therefore, what that means is that for each such orbit, I have a sub-representation pi upper O equals pi upper O sub G. Okay, so that's, in fact, we obtain a decomposition of pi sub G as a direct sum of pi upper O's. There's infinitely many orbits because it's a discrete group acting in a real vector space. And but anyway, this pi G has this direct sum decomposition. Okay, now the definition of pi upper O only involves, so under the action of W, the central element delta doesn't move. So the point is that the definition of pi O involves a fixed central element or a fixed exponent, let's call it Q sub S to the XS delta. And also it only involves a finite number of values, gamma J, of the G functions. So my GI were, functions from the real line to the field, or I don't know what. But if I restrict to an orbit O, then I don't care about the whole function. So each pi O only has a finite amount of data. So what this means is that I can define pi O over the generic field K sub O, which is rational functions like Q and the Ki and the Qs and the gamma J. So finitely many rational functions and a finite number of parameters. Okay. So part 2 of the theorem. So then I can look at the operators Y kappa upper O. Those are the Cherednik operators, which are pi upper O of Y kappa. They can be simultaneously diagonalized on XO. And the common eigenspaces have dimension 1 over this generic field K. So these common eigenfunctions are our generalizations of Macdonald polynomials. Okay, so yeah, that's how it goes. They depend on. Yeah, go ahead. Who's asking?
Siddhartha, how do you want us to think about the gamma J's? I was imagining them to be like the integer special values of Gauss sums or something like that, but I don't think that's right.
Yeah, I'll explain in a moment. So
okay.
Okay, maybe I'll let me give some examples, and then I can come back and explain this a little bit better. Okay. So sure. I won't explain everything, but I'll be able to say enough that hopefully it'll answer your question.
Okay, great.
Okay. Okay, so that's the story, right? So these are our guys. Write down this quasi-polynomial representation. You take a piece of it, and then you get some formula. Okay, I should point out that, okay, maybe not. So there's a lot more to say, and we say it in our paper, but let this suffice for now.
Siddhartha,
Yeah.
what were the parameters I think you were going to say they depended on?
Which parameters, Henrik?
The generalized Macdonald polynomials you have, what parameters did you say they would depend on?
Q, Ki, Qs, and gamma j.
That's all.
Yeah.
Thanks.
Right. I mean, I just kind of explained what are the parameters right here. So you look at the definition of pi O, and the G functions have some periodicity. So okay, there's only a finite number of values of the gammas that will be involved in this formula 4. Okay, you have gi of e for e's, certain e's, only those e's that are in the Weyl group orbit, affine Weyl group orbit of in the Weyl group orbit O. And it's not all things because of this periodicity.
And in the Macdonald QT parameters, Q is Q and T is QS?
Yeah, Q is, so Macdonald has some notation, and okay, Macdonald has some notation in his book, right, or in his papers. So Q has some very specific meaning, and then he has some other parameters that are called T. Okay, so the K's are the T's in the Macdonald setting. In Whittaker function theory, the Q disappears and the T is called Q sometimes. We do what we want, right?
Right. No, yeah, that's good. Well, thank you.
So here the whole point is that there is a Q. Right?
So
Also,
the standard ones you would label by some weight mu, right? What would you label them here? Is it still
by a coset, by an element in capital O.
In capital O.
Yeah. So they're quasi-polynomials. You see, O has, so you take something, and W has a large part, which is just translations.
I see.
So in fact, what you can do is, so, okay, I don't know. All right, maybe I'll say this before moving on. So if you look at the action of W on E, then the quotient, the fundamental domain for the action is precisely what's called an alcove, or a fundamental alcove. So therefore, these orbits O, they correspond to points in the fundamental alcove. You have a section. And the formulas are sort of constant over faces of this fundamental alcove. So there's not that many things. So if you just work with these parameters, then it looks like a lot of things, but there is really something going on over. So yeah, there's not that many of these things. Okay. All right. So okay. I don't know, Henrik, did I explain to you what you were asking?
Thank you. Yes, I was a bit confused, but now, thank you.
Okay. Yes. Yeah, so any other questions? And I also see that I'm calling it generalizations of Macdonald polynomials. My bad. Okay. Okay, so so now I have just a bunch of remarks and some tables. So the first point is, if this W orbit that I was talking about is actually contained in the rational points. So E was the real points. And if it's contained in the rational points, then I can think of our generalization, then we can think of our generalizations with Macdonald polynomials as, now I can think of them actually as elements of a group algebra of some lattice L prime, which is finite index in L. So namely, there are some bounded denominators. So I can go to the lattice with those denominators, and it will have finite index in L. And now here in this situation, if I take the Q parameters and I send them off to infinity in some fashion, then this is going to yield the polynomials that, well, the generic polynomials that Chinta and Ganus were talking about. So I have to get rid of the Q parameters, send them off to. And there's also some twist, but never mind the twist. Modulo this, playing games with the long element of the Weyl group. Two games, I guess. And then now if you further, now in this setting, if you further specialize the G parameters to suitable Gauss sums, then you get the Iwahori, Metaplectic Iwahori Whittaker functions. First, you have to go send the Q parameters off to infinity, and then you specialize the G parameters to Gauss sums. But you're working in this lattice situation. Right. So, okay, so maybe now I can say a little bit more. So the point is that you look at these Iwahori metaplectic Whittaker functions, and okay, you have some metaplectic cover, some degree of metaplectic cover. But now if you look at a polynomial, and then you can say, all right, well, I was working with a smaller lattice, so I have some partition, but there is some sort of stability in these polynomials. Namely, if you say, I don't know, for example, let's say you take the polynomial for some weight n lambda, which has metaplectic degree n. Well, if you just rescale, I mean, if you just took monomials to the, you took the xi to the power n, then it's just the Macdonald polynomial. So it looks like there's a lot of them, but there really aren't. And that's already kind of baked into the discussion that I'm having right now. This kind of stability that you see. So I'm not kind of saying, okay, so if you don't really know Whittaker, if you didn't play with these Iwahori Whittaker functions, it doesn't matter, but if you did, you understand what I mean. Right, so this stuff, yeah, it's only when you make the connection that you realize that this is what's going on. And also, there's like plenty of Gauss sums. But in fact, what's true is that if you take any specific Iwahori Whittaker, metaplectic Iwahori Whittaker function, it can only depend on a bounded number of Gauss sums. Like just universally bounded. There's some bound, which is maybe the size of the Weyl group times something. We would have lots and lots of Gauss sums. And also, there's not that many polynomials, there's not that many formulas, and all of that is kind of easy to see from this perspective. Okay, so all right, so okay, here are some kind of tables for these. Yeah, maybe so these tables are kind of not new, so I don't know if I should even go through these tables. I mean, they are in my so there's a link to my first paper with Jasper and Vidya, and those tables that I was about to show you are from there. Okay, maybe I'll show them because maybe not everybody has seen them. Okay, so the metaplectic polynomials, the way they show up in the Whittaker setting, there is some n, which is the degree of the metaplectic cover, and then you write them as ordinary polynomials. And yeah, so okay, so here are just some examples of these metaplectic polynomials for GL3 of weight at most 2. And the thing with the superscript 1 is simply the Macdonald polynomial. So is it when there's no covering going on. So here is what, so this is the Macdonald polynomial depending on a K and a Q. This is for GL3. And here's how these guys behave. Right. So they're normalized so that somehow the leading coefficient is 1. And here are some more. Yeah. So yeah, so they all look about the same complexity. Okay, but when you go here, so now you see that the Macdonald polynomial is actually the most complicated. The others sort of drop off. And Jason explained the formula for these things in the case of GLN. I'm just showing some pictures for GL3, where he had them expressed as sums over Alkov walks, and many of the features that you see in this table are, you know, they are completely explained by Jason's formula. So here's another one. The Macdonald polynomial is pretty complicated, and then we have this. Now, I point to you, okay, so the stability that I was talking about. So if you look at E2020, it has this expression. But this is in fact just a Macdonald polynomial E1010 in the squares. That's the point. So, I mean, if I scroll back to that picture, you will lose this, but that's what it is. That's the kind of stability you have. Or this will be the Macdonald polynomial, I think E2 at 0, 1, 0 will be this guy. So that's the point.
And the gamma J's again are what you want to think of as sort of associated to like the G1s and G2s in this context?
Yeah. So the notation here is slightly different, but it's the same parameters.
Gotcha.
Yeah. Yeah, the gamma J is probably, this is some old notation from SSV1. What I was describing mostly was SSV2. And there's a link to SSV1 on the seminar page. Okay, here are some more metaplectic polynomials. This guy is like this Macdonald polynomial has a lot of terms and some of them die out. And whenever you have, whenever, you know, this is divisible by the metaplectic, degree divides or there's some GCD between the metaplectic degree and the lambda, you will see things that are purely in the GCD powers of the xi's, and that's the stability. That's already baked into the pi g's. And okay, so I think that's it.
Okay, listening, Siddhartha.